Well, good morning, AP Physics. Welcome to your notes on angular momentum. We're going to split this up into two lectures. That's a little squidgy, but you're kind of used to my terrible handwriting by now. All right, so this is going to be number 1 on angular momentum. Now, just kind of to remind you where we've been, we have taken all of the topics from linear motion and we have started to turn them. So we began with kinematics and we were able to start moving things in a circle. And then we looked at energy because it was a little bit easier. And then we headed on into forces, which were a little more challenging, without a doubt, torque and rotational inertia and all that good stuff. And this is our last big topic of motion that we need to now start to turn, and that's momentum. All right, so we're going to take a look at what is known as angular momentum. Or rotational momentum, but angular momentum is what you're going to see the most. So let's begin with a comparison. So I'm going to make this into 2 columns, and then we'll start comparing the two. Okay, so if you think way back to where we began with linear momentum, and this is how Isaac Newton did it. He took his second law and he broke it up into really the change in velocity per unit time, and then got rid of the time on the bottom and came up with what was known as his impulse formula, or his impulse mode change in momentum. And he said, okay, that is what we call impulse. In order to change an object's momentum, although technically, because we've got that little delta in there, it's the momentum change. Right? So in order to change an object's momentum, we have to apply an impulse. We have to apply force over a period of time in order to make something change its momentum. And we're going to use, along the same lines, the same sort of logic when we get to rotation. This was about changing momentum. When we defined momentum all by itself, we're not changing it. We just want to know how much we have. We use the unit, or the letter P, for that, and it was simply the mass times the velocity. Our units went like that. All right, nothing simplified, nothing was glamorous and elegant and, you know, some new name. Oh, this is called the whatever. No, it doesn't happen. All right, but this is kind of where we are in terms of linear. Now, if we take the same logic and we apply it to rotation, what do we get? All right, well, instead of force, we know that the rotational counterpart is torque. Instead of mass, we know the rotational counterpart is moment of inertia or inertia. And instead of linear acceleration, let's say angular acceleration. So you can probably predict where I'm going here. What's the definition of angular acceleration? Well, it's the change in angular velocity per unit time. And let's move over the t. Right? So this is what I would consider a rotational impulse. If I want something to change its rotation, well, I'm going to have to apply not a force, but a torque. And I will have to apply that over a period of time. All right, my change in angular momentum, ooh, I might have a definition for what angular momentum is, right? So angular momentum change is over here. So what do we know then? Well, if that logic holds from here to here, this tells me that angular momentum is going to be I times omega. All right, so it's going to be, instead of mass times velocity, we're going to do inertia times angular velocity. Now, the symbol they use is capital L. No idea why. None. It just simply is. In terms of the unit, let's consider what we have. So when you, sorry, let me put this one over here. Okay, so inertia. We just did this one, right? Kilograms, because it's mass times radius squared. This guy is going to be radians per second. When you do the, when you multiply those two together, the radians goes away. Why? Because it's dimensionless. Not because it's not important, but because it's dimensionless. I think I may have mentioned that once or twice. So what we end up with is this as our unit for angular momentum. It's, again, clunky. There's no really elegant solution for that. All right, now, I am going to put a caveat by this one. We're going to put a big old star by, oh, sorry, not there. That's not where I want the star. I want the star here. This is what I want to tell you, people. Okay. This formula is one of two formulas for angular momentum. This particular formula is certainly important, but it is for a solid geometric object only. All right, it is not a point mass. I'll put that over here on the right. We have a separate formula for that. So keep that in mind. We have two, and you have to really consider, what does your object look like when you are going to figure out your angular momentum. Okay, so that's the very beginning. All right, taking it from a linear standpoint and then looking at it at a rotational standpoint. What I want to do next, if I can get out of my own shadow here, is to make another slide. There we go. All right, so if point masses are different and we have to do different things with them, what is going to be my angular momentum of that point mass? And that's where we go next. That is where we go next. Okay, so angular momentum of a point mass. Okay, now I'm going to put a big old star. We're going to start out here with this. All right, so all, triple underline that, all points or point masses. Actually, yeah, let me rewrite that so that looks a little better. There we go. All point masses can be considered to have both an angular and a linear velocity, or I'm sorry, momentum. Sorry, I know this isn't picking up every single thing, but I hope you get what I'm going for. Even if only moving in a line. This part really throws folks for a loop. I mean, I can't lie about that. So let's write it and then stop, go back, let's think. So we're saying that all point masses, some blob traveling through space, all right, the wad of chewing gum that comes out of nowhere and hits something and sticks to it, all of those point masses, we're going to consider, well, it's moving, so it's going to have a linear momentum, but it also has an angular momentum. But how can it have an angular momentum if I'm moving in a straight line? That doesn't seem to make a lot of sense. What are you actually saying here, Grady? What I'm saying is, let's say I have this object and it's going like this, right? It's got some linear velocity, right? I can take pretty much any reference point. Let me rewrite it over here, right? So let's say that's, again, there's my velocity. But now instead, I say, well, but this is, you know, I have this object and it's turning and it's right there, or the majority of it is right there. Well, I can draw a radius, honestly, from any given point. And now, as long as I put it in connection to some sort of a radius, I can define this mathematically as having an angular momentum. The reason this becomes important is because when you're solving problems involving point masses, they're often not rotating at first, but then they hit something and they begin to rotate along with it. And one of the key things about angular momentum that is a big deal is conservation. We know that regular momentum is conserved, but let's consider, okay, I didn't spell that right. Sorry, there should be an R in there. And I don't even have space to write it. So, oh well, c'est la vie. You write it in and figure I'm a terrible speller. I don't care. All right, so this is because of conservation. If I have something moving in a straight line and it hits an object and it begins to rotate, it is critical that you conserve your angular momentum, right? I can't say, oh, this thing had a linear momentum and then smack, it changes into angular momentum. That does not happen. You conserve, meaning I have angular momentum at the beginning, before the collision, and I have to have angular momentum at the end of the collision. So this doesn't work. So I have to have two. I have to have both. Okay, so since I can't like magically convert one into the other, you have to consider that even if it is moving in a straight line at first, you can always define it relative to some radius. And that's, it seems like I'm just beating this point to death, but I am telling you, you are going to need to be able to do this. So there's a reason I'm beating it to death. Okay, keep that in mind. Now, so key things, again, angular momentum is this rotational momentum. So instead of thinking about a point or an object moving in a straight line, now we're generally looking at an object moving in a circle. And because it has mass and velocity, or in our case, if we look at it from a rotational standpoint, it has inertia and angular velocity. Therefore, it has angular momentum. If you have a solid geometric object, you have a very simple formula for that. It's going to be the inertia of that object times the angular velocity. If it's not a geometric object, you're going to use this one, this L of a point mass, or angular momentum of a point mass. And you're going to, maybe a formula might help. Geesh, all this gabbing, and I haven't even told you how to find the darn thing. All right, in this case, it's just going to be your linear momentum times that radius. That's going to be the angular momentum of your point mass. And actually, that's I hope with this long-winded explanation kind of makes some sense, right? Because if I make all this big deal about the thing just having, this linear momentum of mv, well, put it in relationship to the radius and you should be fine. Okay. So our two ways to do our angular momentum, and as you can see, we conserve it just like we conserve regular linear momentum. All right, last thing I think for this first round is to talk about direction. But let me double check all of my little notes. I've got notes all over the place. Make sure I don't forget anything giant and important. Okay, so this is our big introduction. Got my point mass. Now I just have to find my one with direction. So finding the direction of angular momentum is actually, it's a little strange. And we don't do it often. You'll do this a lot more in college, most certainly. I've heard all sorts of things about that, but we use what is known as the right-hand rule. So if you want to get a head start on writing that down, I'm trying to figure out where I actually put the darn thing. Right hand, oh, there we go. I found it. I found my stuff. Okay, this is going to be very difficult to do without being in person, but of L. So if you want to figure out the direction of the right-hand rule, we have to, or the direction of the angular momentum, we use what is known as the right-hand rule, and there's more than one right-hand rule, just to make it a little more confusing. But the right-hand rule we use to find it because it is perpendicular to, let me find it. I'm trying to remember. It's perpendicular to both the radius and the velocity. So it's kind of out there in a third dimension. You got to be careful with it. So let's say, there's no way I'm going to be able to draw this, but I want you to consider a better looking wheel than that. Let's say that's a bike wheel, right? And so it's got the spokes, right? And let's say it's rotating that away, okay? And that's, of course, the axis where you would be, assume you have a hand, you can actually hang on to the bike wheel. It would be, you'd be hanging on right here through the middle of it, right? Okay, so the right-hand rule, the first right-hand rule you're going to obviously use, guess what? Your right hand. We're going to do all this with the right hand. Okay, so you want to take your fingers and you want to point along the radius. I'm going to write all the rules down and then we'll go over the bike wheel, okay? Because this is going to be crazy enough. I know I'm not going to be able to draw it. And then the second thing you want to do is you want to curl your fingers in the direction of the linear momentum, which is a fancy way of saying the velocity, really. Not that they're the same thing, but let's face it, what's linear momentum? It's mass times velocity. The mass isn't in a direction, so it's got to be in the direction of the velocity, right? And then here's the key here. How do you know what direction? Because now you're doing this crazy contortion. Your thumb is actually pointing in the direction of the angular momentum. Okay, so let's figure, right? You're going to point your fingers along the wheel, along the radius of the wheel, and if it's spinning this way, right? So the velocity then is in this direction, so you're going to curl your fingers in this direction. And if you're doing this and you're like trying it on the computer screen or whatever screen you're looking at, your thumb should be pointing back at you, right? Your thumb should be pointing back at your face. That is the direction of the angular momentum. It is out of the board, like perpendicular out of the board pointing toward you. If the bike wheel is pointing is going this way, right? Let's say we spin it in the opposite direction. Well, when you do it and then you turn your fingers in the direction of the rotation, your thumb should be pointing into the computer screen, right? Or into whatever screen you're using. That would be the direction of the angular momentum. Do we use this a lot? Not so much in here, but you do use it quite a bit, I believe, in your college level classes. It's worth a mention. You're not going to see it on a free response question, but it's good to know that there is a rule so you can figure it out. And it's kind of a weird one because it goes in, it's perpendicular to two different things. So keep that in mind. I think that's going to wrap it up. Obviously, we don't have any examples quite yet, but we have another recording on the way. All right. Thanks, guys.